I kind of went a different route than we did in the notes. And I didn't write down where I ended up and how I got there. So yes, we are, but we may might just assume what we have in the notes rather than trying to figure out what the heck I had before. I don't remember. Meantime, here's this. John, did you get the email with the homework? I sent out yesterday sometime, but I guess.
Okay, I didn't see it, and it may be that it did get diverted into my spam folder, so now I need to try and figure out where my spam folder is.
Okay. Yeah, it happens to me all the time. So.
I get your emails. I sent you one homework for this week or this last week.
The one that's due this Friday.
But I didn't get that email. I sent you an email before, and I've gotten your other emails, but I didn't get this last one.
Weird. Well, at least one person did, right? Chase, you got it?
Yeah, Ross got it too.
Okay. You got it? Okay, so I'm not totally crazy. I was wondering for a while there. So yeah, check your spam folders. Otherwise, I put it in here, and I'll put it in the photocopy for tomorrow too, for people that aren't able to make it today, just so everyone has it. And if you guys need an extra extension for this one or something, I'll get over that. Homework 7, which I want just now. Oops. Found graded the old one. Oh yeah. Homework 8. Anyone else think they're missing homework through homework 8 or anything? I think that's everybody that is here. We've got the next homework due Friday. I will hand out, I might even hand out homework 11 tomorrow. But it's not going to be due for like a long time. Because like I'm going to be gone forever. So there's not going to be as much of a rush on that one. Okay, so you're talking about non-inertial reference frames, which is all that chapter 9 stuff. Then I got smart. What I thought was smart, and started deriving the tidal equation on my own, and I ended up with a value that gave you, there was proportional to the moon's gravity, as I recall. Did anyone write down what I wrote? Because otherwise we're going to have to pick up from the notes where.
I have your A tidal.
Okay.
I wrote that.
All right, what was it?
It's -2g m scepter thing.
M moon, yeah.
Yeah, over r cubed. Just got James Bond on my inspector.
Yeah.
And then times r e.
Yeah, Earth over.
And this is y hat.
All right, well that's not exactly what I have in the notes, but I think it's going to give us an answer that's
You got ag as well.
fairly close. AG, so gravity, just gravity.
Yeah.
Right, because this R, isn't this R?
That's the
one.
Isn't this R A moon minus RE, right? Quantity cubed? Is that right?
Yeah, I don't have that in the notes. I have an AG below it though, where the R is just a moon.
Yeah.
Cubed.
Oh, so yeah, that's what's being subtracted off. All right. Well, hence, we're going to skip ahead to what I have in the notes, which was all in traits in terms of actually a tidal potential instead of a tidal acceleration. But it's not that different. But in terms of the tidal potential, which I came up with in the notes, it's -g m moon times m of whatever parcel of mass you're looking at. So this is a parcel of your ocean or something over d naught, which is, I'm calling that a moon. This is a moon times 1 plus r Earth squared over a moon squared. So this is the Taylor expansion version, where this is the potential at the center of the Earth would just be this times 1. Tide, the potential is a little bit lower if you're on the side of the moon, side of the Earth pointing toward the moon. Right there, this is the pointing question. Okay. So if you want to look at the differential potential between the center and our point on one side toward the moon, that's going to be negative g m moon m over a cubed raised to the Earth squared. It's not so different than what I have here. Looks like it's off by a factor of 3 halves. I'll have to work on that one. Not sure where that came from. Okay. The important thing to do is that I'm calculating this in terms of a potential, and this is actually important. If you think of a planet, if a planet is perfectly fluid, it's recording, right? It's flashing. It's fine. If a planet is perfectly fluid, then if there's any potential energy difference between 2 points on that fluid, right, it's going to flow from the high potential to the low potential. Okay, so when you have a tidally perturbed planet, if that planet is fluid, it will, the shape it assumes will be an equipotential surface, right? One where the potential energy at all points, including the gravitational potential and the tidal potential, is the same. The reason for that is that if it were different in any place, then you'd essentially have a bump on your ocean, and that bump would flow to the low points and fill everything in. So, if you want to figure out what the total height of the tide is, what you want to do is actually find the equipotential surface that has the same volume as the real Earth, which is a little bit complicated. So instead, what we're going to do is just assume that to first order these differences in magnitude. See, there should be a factor of 2 here. We came up with a factor of 2 before. Anyway, all right. So within the usual Barnes factors, this is close. So to actually calculate the full, what's the height of the tide? So this is the difference in potential that you have in order to figure out the difference in, all right, so this is the potential. What's the difference in force? So what's the tidal force? Do you know the potential? Negative gradient of the potential. So plus gradient with respect to what's changing here, distance from the moon. No, actually radius to the Earth is what's changing. Right, because we're looking at what point you are on the surface. So if you're further away here, this becomes, RE plus delta. So we'll want to take the derivative with respect to RE here. So that becomes 2G M RE over A to the cube. Okay, that's looking more. I've recovered my factor of 2, so that's a positive development. Okay. So this is going to be an acceleration times a mass, right? So this is m. This should be this value, which is pretty close actually, times m should be the acceleration. The potential in Earth's gravity field, if you're at the surface, is about mgh. Okay, we're not looking. Tidal influence of the moon on the Earth is not so big that mgh is going to go wrong on you. So this is going to be mgh. This is what we want to find, height the tide there. So we're going to set that equal to the potential you'd get from the moon's gravity and figure out where essentially the new equal potential surface is that would have the same potential as the Earth's surface with no tides in it. And that's, once again, it's not quite right, but for very small tides, it's pretty good, and these tides are hella small, so it's good. All right, so this should be equal to 2 GM over A moon cubed times, this becomes raised to the Earth plus delta, and delta is what we care about. In fact,
Wait, and a question.
yes,
Isn't that force you put in? No,
this is the force, you're right. So this is mg, this should be this times, well, this, do we need another height term? You might be right.
Well, shouldn't you be using u diff, not f diff?
Yes, that'll end up the same thing I said, but let's do that anyway. Right, because you multiplied it by another times, another that term, that's where you get, okay, so G M RE squared over A moon cubed. Of course, we want these to equal their opposites. We want the magnitudes to be equal. By moving up, you're of course going down, you're losing potential energy with respect to the moon, but you're gaining it with respect to Earth. We want those to be equal, so I'm not going to worry about the minus sign. We're going to solve this for height of the tide. That doesn't matter. G of the Earth, of course, is GM Earth over R Earth squared, right? So let's plug that in. The height of the tide, therefore, is going to become, we're going to have a G on both sides, so it's not going to depend on G directly. We're going to have a mass of the moon over mass of Earth here. So the major axis of the moon is still going to be here, cubed. There's got an RE to the 4 here. And I'm probably missing a factor of 2 somewhere. Okay, this actually says I'm missing a factor of 3/2, so we're going to assume that that's right, but in truth, this isn't actually quite right either. And this is off by a factor of 2 for sure, because, all right, to get into detail, this is what will give you the height of the tide in a static case, where the moon is just sitting there and the Earth is sitting here, and they're both falling to each other. Of course, that's not what's happening. They're both rotating around the center of mass of the Earth-Moon system. So actually, as we're going to talk about later this lecture, there's actually a centrifugal term here too. It corresponds to how differentially fast the center of the Earth is right? The center of the Earth here has to go around, is orbiting around the center of mass, and so is the far side of the Earth, but the far side of the Earth has to orbit around this, further around the center of mass, and so it has higher centrifugal force, actually, that pushes it out. And that, if you calculate that out, it actually happens to be the same factor, so there should be 2 of these. This exact distinction actually always trips up people in their PhD oral defenses in my old planetary sciences department, and usually gets the committee fighting about what's going on and whether that's true or not. So this is true if you just stick the moon and the Earth and you let them go. If they're orbiting around, it's higher by a factor of 2. But let's look at this equation and look what it's involved. First of all, it doesn't depend on the gravitational constant G. That's because both Earth's gravity and the moon's gravity are both involved, and those G's are going to cancel. Depends on the mass of the moon. It's proportional to the mass of the moon. Okay, that's not too unexpected. So if you double the mass of the moon, you double the height of the tide. It's inversely proportional to the mass of the Earth. So more massive Earths can pull that tide back, and the relative influence of the moon is smaller. So this factor isn't too unexpected. These factors are kind of unexpected, I think, okay? First is semi-major axis of the moon cubed. So the distance from the Earth to the moon cubed. And this ultimately, the way I think of this, like I said before, is that this is sort of the derivative of if you calculate the gravity of the moon, it's gmm over r squared. You take the derivative of that, and that's the slope of the line, and that it goes as r cubed. So tides are the first order correction to our assumption that all the mass of the Earth or all the mass of the moon is concentrated at a point mass at its center. It's the first order correction, and as the first order correction, it goes as r cubed. Are there higher order corrections? Yeah, if you want. So far, we looked at the Earth's shape relative to the moon, and it comes out, looks like a pill that way. But it's called a prolate spheroid, okay, where it has a given radius here, and then its two other radii are identical. So this is, imagine an ellipse in 3 dimensions with different, so an ellipse in 2 dimensions, right, has a semi-major axis and a semi-minor axis. In 3 dimensions, we call this a triaxial ellipsoid. There's 3 different dimensions, but the ultimate shape it gets pulled into has 1 large dimension pointing toward and away from the moon, 2 small dimensions pointing the other direction. So this is the first order correction, and it's perfectly good for the moon's influence on the Earth. If, on the other hand, you get, say, a star, and then you have a gas planet orbiting really close to the star, and these happen. In fact, there was one that I'm on a paper looking at. This planet is about 2/3 of a Jupiter mass, and it's less than a stellar radius away from the star. Its year is 11.8 hours. That's crazy! We see this, but this stuff exists, okay? So in that case, you need the higher order terms, okay? The whole just r cubed doesn't work anymore, and this thing ends up looking like more like an egg, where the side that's toward the star isn't the same shape as the side that's pointed away from the star. You can also get contact binary stars, so 2 stars that have migrated due to tides. We'll talk about how that works in astrophysics, but they get such that they can get to be such that they're touching. You can get a star that kind of looks like this. Because the tidal envelopes of both stars essentially start to merge once you get them close enough in. And that also is where this 1/a cubed is no longer good enough, and you need to do either a full treatment or go out to higher order terms to get more in there. Incidentally, what does this look like? What other astrophysical object does this look like? Anyone seen this? Yeah, this new comet, Churyumov-Gerasimenko, which is this comet that the Europeans have an orbiter, Rosetta, that's looking at, and they sent down the lander. And they're trying to find a place to send the lander on this. Can you imagine what the gravity field looks on this? It is a nightmare, okay? What are the slopes, right? I mean, you have to figure out which direction the gravity vector, you don't want to land on, put your lander down where it's going to slide downhill. How do you calculate even the slopes on something like this? I mean, you have to basically treat it as a set of individualized chunks, right? Little voxels instead of pixels, and put them all together and assume that there's no porosity. Probably a bad assumption in a comet, and try to figure out what's going on. It's a horrendous nightmare. But that particular comet looks like it's essentially one of these. It's a binary that's somehow managed to merge. 2 comets have managed to merge. And then all the dust that's fallen in between since then has sort of filled in the gaps, and so it looks like this. Actually, it looks like a rubber ducky, if you look at it in detail. So they ended up landing on the head of the rubber ducky, okay? Here's the place where you know where the gravity points. All the mass is this way. So there's no ambiguity here. You know which way the gravity points. You can actually solve this problem. If you want to try to land here or something, oh my gosh, don't even do that. That's too hard. So they tried to land somewhere simple, and even that didn't work. Because, of course, the gravity on this comet is, I think, millimeter per second, a couple millimeters per second squared. So you could essentially jump, and you'd easily achieve escape velocity. So the problem with their lander was how to stick to the comet. So they actually had 3 different ways to stick to the comet. Okay. First of all, they had engines pointing up that would push them down. Usually, right, if you're landing on a planet, the engines point down to prevent you from crashing into the planet. No, not on a comet. You got to push down to hold yourself down. Then they had harpoons that stuck out and went pa-chunk. They were supposed to hold them onto the comet. And then they had screws. Each foot had screws that were going to screw in and hold themselves down. Each one of those systems failed, and so they bounced off and actually came to rest maybe a couple hundred meters from where they expected to be. And unfortunately, they're in next to this cliff that was blocking them from the light, and their lander never did get enough sunlight to recover. So there you go. So, long story about A naught, about A cubed in the denominator. Here's another interesting factor. It goes as the radius of the Earth to the 4. It's pretty high. Another way to look at this is plus some factors of 4/3 pi somewhere, right? What would it look like? 4/3 pi, I think, something like that. 2 pi, okay. So one way to think of it is it goes, for a given mass, it goes as the radius of Earth to the 4. Another way to look at it is that for a given density, it goes as, it's proportional. The size of the tide is going to be proportional to the radius. So lower density planets or fatter planets can really show much stronger tidal effects. Hence, if you have a gas giant that's very loosely holding on to its outer layers, it's going to be really easy to distort as compared to a very massive body. It's going to be very difficult to distort. Does that make sense? All right. This is the one lecture version of 1.2 lecture. Oh my gosh, 1.5 lecture version of tides. If you want more, you'll see plenty more in astrophysics. Okay. So what we're supposed to talk about today, it's okay, I think I'm a lecture ahead, so we're good, is centrifugal force. Or we talked about motion in this tidal frame, which is in which the Earth's center is falling toward the moon. Now we're going to talk about motion in generic rotating coordinate system. Okay, so rotating coordinate systems can be, somewhat helpful in many different contexts. One of them is, of course, the one you're sitting on. Okay, we all think that Earth is static. People thought that Earth was static for many years, right? The ancient Greeks knew. They didn't just think, they knew that obviously all the stars and the sun revolved around the Earth, because I don't feel like I'm moving. Do you feel like you're moving? Okay. Bogus. Turns out you can't feel motion, so it doesn't matter. But if you're on a rotating coordinate system that seems like it should work, you should be able to use it. You can use your non-inertial rotating coordinate system here of the Earth and still derive equations of motion that work in that non-inertial coordinate system if you tweak it a little bit. So let's do those tweaks. So if you have some inertial coordinate system, which we're going to call S naught, that's a right-handed coordinate system, right? Yeah. Okay, good. This is inertial. And we're going to assume that you have some new coordinate system Why do I have those X, Y, Z in funny angles? Doesn't make much sense. All right. But the new coordinate system is rotating at some rate omega. So I'm going to call this omega vector. Has anyone seen a rotation rate as a vector before? No? Okay. I should explain it then. So basically, if you have any object that's rotating, some cylinder, usually you give its rotation maybe as lowercase omega. But if you want to represent that rotation in three-dimensional space, you sort of need to have a direction associated with it. So this capital omega vector is equal to the same rotation rate that you're familiar with times some direction vector that corresponds to essentially your thumb, where your thumb points in the right-hand rule. So wherever you are in space, you have an object that's rotating at a rate lowercase omega. You curl your fingers in the direction of that rotation, and your thumb points in the direction that the rotation vector points. So this is just the same as saying you have something that's rotating at a rate omega, but in addition to telling you the rate at which it's rotating, the capital omega vector is also telling you, the direction of the rotation, essentially. Okay. So there's a whole couple of sections in the book that I am going to not derive. And that is, say you're in this new coordinate system that corresponds to, has some new z, new x, new y. But it's rotating. This new coordinate system rotates with respect to the inertial coordinate system at this rate lowercase omega, or at the in the direction of capital omega vector. So the book spends two whole subsections trying to tell you how to do a time derivative in a rotating coordinate system. So if you're looking for a way to get to sleep at night, please do read those sections. I didn't think they were terribly illuminating, and so what I'm going to do is I'm just going to show you the result of how to take a time derivative in this rotating coordinate system, and then you can read the reason why this identity works on your own. So the idea is, say you have some vector, it doesn't matter what this vector represents. This could be a position, it could be a velocity, it doesn't matter what it is. You have some vector q, and it's in, you want to know what the time derivative of that vector is. And you want to know what the time derivative is in the rotating coordinate system, or in the other coordinate system, it doesn't matter. If you want to take the time derivative, this is what it looks like. If you know what it looks like, or you know how to do it in an inertial frame, because that's simple, you don't have to do anything fancy. In order to do it in a rotating coordinate system then, to get the derivative right, you need to take the time derivative in that rotating coordinate system of q in the new coordinate system, plus you need to account for the rotation. And the way you do that is you take the rotation vector, which is a direction, but also it has a magnitude. So what are the units of that rotation vector?
Per second.
Radians per second. So effectively that effectively kind of acts the same as a time derivative, right? It's going to add an extra time, per unit time on the bottom. You cross that omega vector into the vector of interest. And doing so allows you to get a complete derivative. So if you think about this, this is very similar to what we showed on Monday. We were looking at, if you want to convert a rotating coordinate system in 2 dimensions, how you get that by subtracting off essentially the rotation. Yes?
So this is saying the time derivative of q in the inertial reference frame is this?
Right.
Okay.
So you want to figure out, in general, what the time derivative, if you want to figure out the time derivative, you need to figure out the time derivative in inertial space. Because if you're just doing it in a rotating coordinate system, it's non-inertial and it doesn't work, it doesn't compute. So the idea is, if you want to take a time derivative in a rotating coordinate system, it doesn't look like this, you have to do this. You take the time derivative of the strict vector coordinates in the rotating coordinate system. You add in this factor that compensates for the factor in a non-inertial rotation, a non-inertial frame, by accounting for the rotation.
So you don't even need to worry about rewriting Q in the inertial frame.
Right. That's the advantage. Well, I mean, yeah, so, right, you take Q, these are all Q, I should probably say Q in S, right? This is Q in the rotating coordinate frame already. We've already dealt with that. So that's the advantage, is because frequently, like if you're on a rotating Earth, you want to know what, say, your position is. You have your position. And it's real simple in your rotating coordinate system, because you're sitting here in a room and you're not moving in the rotating coordinate system. Alternately, if you were doing this in inertial space, you'd have to have a complex motion that's a function of time. It's not that complex, but you could imagine how it would get nastier as you progress through trying to treat any reasonable system that's in a rotating frame. So actually, we use this more often than you might expect. For instance, in astrophysics, if you want to know how if you have two planets, say, and a star, you want to know how that's going to behave, it really frequently gets much easier to treat this whole system instead of an inertial space, to just say, okay, so you have a planet and a star, and then this planet's in a circular orbit. We're just going to put yourself in a rotating coordinate system where the star and the planet are fixed. Then you can treat everything else relative to those if you include this extra factor for the rotating coordinate system. You don't have to do it in the original set of coordinates. Okay, here comes the gross part. So, say we're going to pick, this was a Q in general here. Let's take a specific vector now. We're going to call this new vector R. Just call it R, and you can pick which coordinate system you want to do. So if you have a position vector R, and you want to figure out, say, the equation of motion for this guy, we're going to need to figure out the acceleration. We're going to need to take two time derivatives, hence when we need to use this factor, okay? So let's do that. Ultimately, we want to find that's what we're trying to get. So how are we going to get there? Let's take the first derivative first. So dr dt, full derivative in inertial space, is going to be equal to dr dt, dr vector dt in the rotating coordinate system plus omega crossed into r. Well, duh, that wasn't too hard. It's just taking what I told you was true and that you get to read while falling asleep tonight, or falling asleep this afternoon if you read it then. Either way, it works. For why this is true, but converting our position vector, taking its derivative in the rotating coordinate frame, that's what you get. Okay, so let's do it again. Now it gets a little hairier. Okay, so we want to take this derivative of this first term. So that's going to be a d by dt of dr dt in the rotating frame plus omega cross dr dt. I'm just applying this sort of in a nested fashion. The new q is this whole vector. I'm going to treat each term separately. So first, this is the new q. So dq dt, d by dt of this whole thing is equal to dq dt in the rotating coordinate frame of this vector plus omega cross q, which is dr dt. Okay, that's half of it. And we need to do the same thing for this term. d by dt of omega cross r plus omega cross r. do that right? Yeah. Kind of ugly. Yeah, this is okay, right? Omega cross r has to be perpendicular to omega. So this can't come out 0, right? Not as bad as it looks. So it does look kind of bad, I admit. Okay. Okay, so this is just in the rotating coordinate frame plus omega cross dr dt, but if you look over here, we're assuming that the rotating coordinate system is rotating at a constant rate. So omega is not a function of time. So this becomes omega cross dr dt as well. So there's two of those, 2 omega cross dr dt's, and 1 nasty omega cross r. Okay, so rewriting this and multiplying both sides by m to put this in force space, so this looks like an MA now. Okay, MA in inertial space, so the full MA is going to be equal to MA in rotating space plus some extras, some bonuses. Those bonuses are a 2m omega cross r vector dot and an m omega cross r. Why did I get that?
Yeah, you have to order screwed up here.
Yeah, why do you suppose that is? What do I do? Here's 3. Here's page 3. Yeah, it looks like omega cross r here. It looks okay at this point, but then suddenly I flip it in the next line. Why did I do that? Oh. Yes, got it. Because I got these flipped, that's why. No, I think it was right. Hold on. Okay, it was right. But what we really want to know is the motion in the rotating coordinate frame, in which case I'm going to move this to the left side. This becomes mr double dot. This corresponds to the motion in the rotating frame is equal to MA in the inertial frame. In the inertial frame, MA is equal to the force. So this is the force, the conventional force on the object. And then, right, because, okay, yeah, these are on the opposite side. But in order to split the sides of this and solve for here like I did, you have to subtract these off, and that's where those flip. Okay, so to subtract these off, you could say minus, or we can say 2m, and then switch this to r dot cross omega instead. All right, I was wondering where those came from. And then this becomes, instead of omega cross r, then we get omega cross r cross omega. Okay, there we go. Okay, so this is what F equals MA looks like in a true rotating coordinate system. Okay? MA is equal to the inertial force. So this, whatever force there would be in a normal system. So in a non-rotating system, right? If there was some external force on this guy causing it to move, that's the same force. So in the rotating system, you get the same reaction due to a force that you normally see, plus some interesting extra terms. One that depends on velocity, and that's the Coriolis term. One that depends on position, and this is the centrifugal term. All right, and I think I'm going to leave it there, and we will start looking at the centrifugal term first tomorrow morning, because it's a little more straightforward. Because it depends on position, right, and not on velocity. A little simpler. And then on Friday, we'll look at the Coriolis term. We might actually even get started tomorrow. So thank you guys for coming. I know these additional lectures are kind of a pain, and I really appreciate that you guys are here. And I appreciate if anybody's watching it, appreciate that too. So see y'all tomorrow. We are getting fewer people showing up at these as a function of time, I guess. Yeah, I've got lots of extras now. I'll get over it.
I don't think your gratitude was mine.
I think you're right. We will take it up there and make it disappear. They'll appreciate that you're looking out for them.
Well, they're starting too.
Yeah. Well, you know, if I pay them too much, they get, start to get complacent. Gotta keep them hungry.